Number one, this question asks you to investigate models for the populations of trout in a lake. Trout is a type of fish. At the start of a year, a lake is estimated to contain 6,000 trout. The owner of the lake estimates that the number of trout will increase by 10% per year. At the end of each year, the owner proposes to remove 500 trout from the lake to prevent overpopulation. Therefore, the relationship between Tn, the predicted number of trout at the start of year n, and Tn plus 1, the predicted number of trout at the start of the year n plus 1, is given by this formula. Tn plus 1 equal 1.1 Tn minus 500, and T1 is 6,000. For example, the predicted number of trout at the start of the second year is given by T2. T2 equal 1.1 T1 minus 500. Use this formula to verify that T2 equals 6,100, right? Well, A. The formula is T1, Tn plus 1 equal 1.1 Tn minus 500. If T1 equal 6,000, so we can determine T2 based on this formula. T2 equal 1.1 times T1 minus 500. It equal 1.1 times T1 is this one, 6,000 minus 500, and equal 6,600 minus 500 equals 6,100. This is T2. Verify that T3 equal 6,210 and find T4. T3 equal 1.1 times T2 minus 500, 1.1 times 6,100, 500, and if you calculate, the result is 6,210. T4, 1.1 times T3 minus 500, 1.1 times 6,210 minus 500, and if you calculate, the result is 6,331. It is also known that Tn equal this expression. Show that Tn equal 1,000 times, this expression we are going to prove. Hence or otherwise, find T6, give your answer to the nearest whole number. Let's see. The given formula is Tn, 6,000, 1.1 power n minus 1 minus 500 times 1.1 power n minus 1 minus 1 divided 1.1 minus 1. It's going to be 6,000 times 1.1 power n minus 1 minus 1.1 minus 1 is 0.1. If 500 divided by 0.1, 500 divided by 0.1 equal 5,000. So it becomes 5,000 times 1.1 power n minus 1 minus 1. 1.1 times n power minus 1 minus 6,000 times 1.1 power n minus 1, because 5,000 and 1.1 power n minus 1 plus 5,000. It is because minus times minus. So 6,000 minus 5,000, it is 1,000. 1.1 n minus 1 plus 5,000. This is the n. And part 2, we are going to find T6 based on this formula. T6 equal 1,000, 1.1 power 6 minus 1 plus 5,000, 1,000 power 1.1 power 5, 5,000. And if you calculate this, the result is 1,610.51 plus 5,000. And if you calculate, the result is 6,000 because it's 1,000, yes, 6,610.51, or in whole number, 6,611. This one. Next question. After deciding that the trout population would increase too quickly, the lake owner proposes instead to remove 750 trout at the end of each year. The relationship between the n, the predicted number of trout at the start of year n, and the n plus 1, the predicted number of trout at the start of year n plus 1 is now given by the n plus 1 equal 1.1, the n minus 750, and the 1 equal 6,000. It's also known that the n equal minus 1,500 times 1.1 power n minus 1 plus 7,500. Show that this one, the n plus 1 minus the n equal minus 150 times 1.1 power n minus 1. So given to formula that the n plus 1 minus the n. The n plus 1 is 1.1 the n minus 750 minus the n equal minus 1,500 times 1.1 n minus 1 plus 7,500. One. Right. So it becomes 1.1 the n minus 750 plus 100 1,500 1.1 minus 1 n minus 1 minus 7,500. This is minus. And it will be 1.1 the n plus 1,500 minus, this is 8,250. The n is this expression. This one. Plus 1,500 and minus 1 minus 8,250. So if multiply, becomes minus 1,650 and minus 1 plus one 8,250. This one 1.1 n minus 1 minus 8,250 and 0. Now minus 1,650 plus 1,500 equal minus 150, 1.1 n minus 1 power n minus 1. So this is n, dn plus 1 minus dn. Part 1. Part 2. Use the result in part D1 to deduce that the predicted number of trout at the start of any year will greater than the predicted number at the start of the next year. Okay. If you look the result of this one, the n plus 1 minus the n, it is minus 150. The result is always negative number. If negative number, it means we can state that the n plus 1 minus the n always less than 0 because negative. If less than 0, it means we can state that the n plus 1 less than the n, or the n greater than the n plus 1. It means we can state that the predicted number of trout at the start of any year will be greater than at the start of the next year because of this conclusion. Next question, part E. Determine the first year during which there will be no trout remaining in the lake. Okay. We are going to predict it, and when there is no trout anymore. So we need to set that the n equals 0. If the n equals 0, it means minus 1,500, 1.1 power n minus 1 plus 7,500 equals 0, or 1,500 but 1.1 power n minus 1 minus 7,500, or we can set is divided, becomes 1.1 n minus 1 equal 5 because 7,500 divided by 1,500, or according to learn rule that we can write in that n minus 1 ln 1.1 ln 5, or n minus 1 equal ln 5 over ln 1.1. And if you calculate, this is 16.8863. So n equals 16.8863 plus 1, okay, equals 17.8863. So we can state that trout disappear at the end of 17th year, or at the start or at the beginning of 18th year. Next question. The lake owner now considers a more general approach where the trout are removed at the end of each year. Let the n denote the predicted number of trout in the lake at the start of the end year where this equation. Find the value of D such that the predicted number of trout at the start of each year is constant, right? If constant, it means we are going to find Cn plus 1. Cn equals 6,000, 1.1 power n minus 1 minus 10D times 1.1 n minus 1 minus 1. Okay, so Cn plus 1, if constant, it means Cn plus Cn plus 1 equal constant. 6,000, 1.1 power n, because n minus 1 plus 1 equal n, and D n minus 1. So Cn plus 1 equal Cn, equal constant. So 6,000 n minus 10D 1.1 power n minus 1 equal Cn, 6,000 10D is 1. And after that, multiply 6,000 10D times this expression plus 10D 600 6,000, I mean. Okay, this is 6,000 n minus 1. Multiply this 10D n minus 1 plus 10D. So it becomes 0. After that, this expression with this expression, and as well this expression with this expression, we are going to collect them. So 6,000 1 minus 1, 1 times 1, 1.1 n minus 6,000 1.1 n minus 1. And this one we move here, 10D 1.1 for n, 10D n minus 1. After that, factorize 6,000 1.1 or n minus 1.1 or n minus 1. 10D 1.1 n 1.1 n minus 1. And divide it. So it becomes D equal 6,000 divided by 10 equals 600. Next question. To model predicted numbers of trout, the lake owner has been using sequences generated by this equation. Use mathematical induction to prove that we are going to prove this. That un equal u1 r power n minus 1 times 1. Okay. Okay, so un, according to the information, equal u1 r power n minus 1 minus d times r power n minus 1 minus 1 divided r minus 1. Okay. So we need to assume that n equal 1. If n equal 1, substitute n equal 1 into this equation, r power 1 minus 1 r power 1 minus 1, 1 is 1, u1 equal 1. It is equal 1 because r power 0. And this is 0, r minus 1. So it's going to be u1 equal u1. It is true. The next step, the second step, is we are going to assume that n equal k is true. Okay. So this step is the hypothesis step. So uk that we are going to using this formula k minus 1 minus d 1 r minus 1. Okay. And the third step, assume that n equal k plus 1. This is the inductive step. For this inductive step, uk plus 1 equal u1r power k minus d r power k minus 1 over r minus 1. According to the information that uk plus 1 equal r times uk minus d. Okay. While UK is just now it's found on part 2. UK is u r k minus 1 plus 1. Right. So substitute this expression into this expression r times k minus 1 r minus 1 minus d. This is just information, this one. And let's continue. Calculate r times ru1 k for the r power k minus 1 minus r times d rd r power k minus 1 r minus 1 and the r will setting becomes the r minus 1 r minus 1 and this is r power 1 r power k minus 1 becomes 1 r power k because 1 minus 1 and this is d if r times 1 becomes r power k minus r 1 and after that this is minus dr minus d r minus 1. It's going to be u1 r power k minus I would like to write to calculate multiply plus dr minus dr plus d r minus 1 this one d r power k 0 plus d r minus 1 Factorize. So prove that UK plus 1, UK plus 1 equal this expression. Number 2, a polynomial is said to be palindromic if the sequence of its coefficients remains the same in the reverse. This question asks you to investigate some properties and solutions of palindromic polynomial equations. In parts A and B, consider quadratic equation of the form ax squared plus bx plus a equals 0, where a not equals 0. The sequence of coefficients a, b, a remains the same in reverse. The following table shows three palindromic quadratic equations and their sequence of coefficients. This is a table. The quadratic equation 2x squared minus 5x plus 2 equals 0 has roots 2 and 1/2. There's roots from a reciprocal pair, since one root is the reciprocal of the other. So 2 and 1/2 is reciprocal, because if 2 multiply 1/2, it's equal 1. So we call that 2 and 1/2 is reciprocal. Determine the roots of x squared plus 4x plus 1. So if we identify that quadratic equation a equal 1, b equal 4, and c equal 1. So x1 and x2, using quadratic equation formula, minus 4 plus minus square root 4 squared minus 4 times 1 times 1 divided by 2 times 1, or minus 4 plus minus square root 16 minus 4, 12. 4, it is minus 4 plus minus 2 square root 3 half. The x1 equal minus 4, minus 4 plus 2 square root 3 divided by 2 equal minus 2 plus square root 3. And x2 equal minus 4 minus 2 square root 3 divided by 2 equal minus 2 minus 2 square root 3. x1 and x2. Next question. This part 1. Part 2. Give the roots in the form s plus square root 3, where s element of integer and t element of integer plus, hence or otherwise, so that there's roots from reciprocal pair. So look, x1 is this one and x2 is 1. So reciprocal if x1 times x2 equal 1. So minus 2 plus square root 3 minus 2 minus square root 3. If you calculate, this is 4 minus 3 equal 1. So since the product of these roots equal 1, this confirms that x1 and x2 are indeed a reciprocal pair. Show that the complex roots of x squared plus 1 equals 0 form a reciprocal pair. B. So x squared plus 1 equals 0. It means x squared equal minus 1. X equals square root minus 1. Okay, this minus 1 plus minus. So we can state that x equal plus minus this is I, plus minus of I, because square root minus 1 is I, imaginary number. So if x1 times x2 equal I times this positive and negative I multiply minus I equal minus I squared or minus of minus 1. So this is positive 1. So the product of uh, x1 and x2, the product is 1. So the complex roots form are reciprocal here. The reciprocal pair, x1 and x2. Next question. Let Px equal ax squared plus bx plus a, where a not equal 0. Verify that Px equal x squared of times function p I 1 over x. Px equal ax squared plus bx plus a. So if p1 for x equal a times 1 over x squared, b times 1 over x plus a. If we multiply by x squared, it's going to be x squared times 1x, p1x. This is becomes a plus bx plus a x squared. And this expression is px. So x squared p1 over x equal px. So px equal x squared p1 over x. Next question. In parts D and E, you may assume the result that a polynomial Px of degree n is palindromic if and only if Px equal x power n p 1 over x. Use Px xn p1 over x to show that if a not equal to 0 is a root Px equals 0, then 1 over alpha is also root. Px equal x power n p1 over x. So if p alpha equals 0 because of roots of if alpha is roots of, it's implicated to alpha power n times p over 1 over alpha equals 0. So if alpha not equal to 0, so p 1 over alpha equal 0 divided by this expression and it equal 0. So it means p1 over alpha equal 0. Then if p1 over alpha equals 0, it means 1 over alpha is also a root. So next question. Question E. Let fx equal px key x, where p and q are palindromic polynomials of degree n and m respectively. Show that f is a palindromic polynomial. E. Px is x power n p 1 over x, while qx x power n q 1 over x. Okay. So if px times qx It means x power n p 1 over x times x power n q1 over x. So it means it becomes x power n, x power n, x power n plus m. p1 over x times q1 over x. This expression is fx. So we can writing px times qx is x power n plus m times fx. n plus m, m plus m is degree of fx. So we can state that f is a palindromic polynomial. Next question. Consider the palindromic polynomial fx equal x power 4 plus 2x cubed plus x minus x squared plus 2x plus 1. This polynomial can be expressed in the form, this one, by forming and solving an appropriate system of equations in u and phi determine the value of u and the value of phi. F, if fx equal fx, it means x squared plus ux plus 1 times x squared plus vx plus 1 equal x power 4 to x cubed minus x squared plus 2x plus 1. If we multiply, becomes x squared plus vx cubed plus x squared. So that plus ux squared u phi x squared plus ux plus x squared plus vx plus 1 equal this expression, x squared plus 2x cubed minus x squared plus 2x plus 1. It becomes, this is x squared, oh, this is x power 4, x squared times x squared. So x to the power 4 plus u plus phi x cubed plus 2 because, yeah, 2 plus u phi x squared, this x squared, 1x squared, u phi x squared, 1x squared plus this one and this one, u plus phi x plus 1, x power 4, this is 4, plus 1, okay, equal 1, so 0 because 1 minus 1, and now we look this, I just look this u plus phi equal 2, this one. So u plus phi equal 2. So u times this one, u and this one, 2 plus u phi equal minus 1. U phi equal minus 3. Now substitute u minus 3 into this equation, becomes I would like to put it like this, minus 3 over phi. Okay, so minus 3 over phi plus phi equals 2, multiplied by phi becomes minus 3 plus phi squared, minus 2 phi equal 0. And then find phi. This is A equal 1, B equal minus 2, and C equal minus 3. So phi 1 and phi 2 equal 2 plus minus square root minus 2 squared minus 4 times 1 times minus 3 times 1. This is minus 3. So this is 2 plus minus square root. This is 16. Yeah, 4 plus 12. So 2 plus minus 4. So phi 1 equal 2 plus 4 divided by 2 equal 3, and phi 2, 2 minus 4 divided by 2 equal minus 1. Okay, let's continue. To find u, if phi1 equal 3, so u plus 3 equal 2, and u1 equal minus 1. If phi 2 equal minus 1, so u plus 3 equal minus 2. So it means, yeah, u2 equal minus 5. If u less than phi, it means u equal minus 1 and phi equal 3. So this is u, this is phi. Next question. J. Hence, find all the exact complex and purely real roots of x power 4 plus 2x cubed minus x squared plus 2x plus 1 equals 0. G. If u equal minus 1 and p equals 3, so fx equal x squared minus x plus 1, so minus x plus 1 times x squared plus 3x plus 1, because this is ux, this is phi x. For x squared minus x plus 1 equals 0, we will find the roots of this equation, this quadratic equation. So x1 and x2 is 1 plus minus square root minus 1 squared minus 4 times 1 times 1 divided by 2 times 1. 1 plus minus square root minus 3 divided by 2. 4, this expression, x squared plus 3x plus 1 equals 0. We're going to find the roots x1 and x2. So x1 and x2 equal 3 plus minus square root 3 squared minus 4 times 1 times 1 divided by 2 times 1 equals 3 plus minus square root 5 divided 2. So this is the roots, this one and this one, the roots. 1 plus square root minus 3 divided by 2 and so on, 3 plus square root 5 plus 1, and I hope I forgot this one, plus 1 plus minus square root 3 I. Yeah, that's one. Next question. Consider the polynomial polynomial equation of this equation when n is odd. Show that minus 1 is always a root of this equation. H. So the equation is px equal x power n plus a1 x power n minus 1 plus a2 x power n minus 2 a2x squared plus a1 x plus a0 equal 0. Now, if x equal minus 1 and n is odd number is 1 or 3 or 5 or 7, so on. So it means p minus 1 becomes minus 1 power odd number, a1 times minus 1 plus odd number minus 1, a2 times minus 1 power odd number minus 2, a2 times minus 1 squared, a1 times minus 1 plus 1 because x to the power 0 is 1, 2. So if you calculate this is minus 1 plus a1 because minus 1 power, this is odd number minus 1, is minus 1 power odd number minus 1, it becomes positive 1. Yeah, but so this expression is minus a2 on, and this expression is positive a2, and this is minus a1, and this is 1 equals 0. So if you calculate all of this, the calculation equals 0. So we can say that p minus 1 equals 0. If p minus 1 equals 0, it means minus 1 is always a root of px.